I'm Urban Camacho. This is Physics 161, and the problem we're going to be solving today is number 26 from Chapter 9, which is from the chapter of linear momentum and collisions. So for our problem today, we have a situation where in an American football game, a 90-kilogram fullback running east with a speed of 5 meters per second is tackled by a 95-kilogram opponent running north with a speed of 3 meters per second. Now they ask for three things. In A, explain why the successful tackle constitutes a perfectly inelastic collision. B, calculate the velocity of the players immediately after the tackle. And C, determine the mechanical energy that disappears as a result of collision. Account for the missing energy. Now for A, the tackle constitutes a perfectly inelastic collision because in a perfectly inelastic collision, two objects collide and stick together right after the collision and drift off as one unit. They never come apart after the collision. So in this case, as the opponent tackles the fullback, he grabs onto him and doesn't let go of him until the tackle is complete. So that's pretty much how they're considered one unit, because they're always together as soon as the tackle takes place, right until the tackle is over. So now we can go out and answer the rest of our questions. So for this problem, we're going to consider our mass 1 to be our fullback and our mass 2 to be our opponent. And as we heard in the problem, mass 1 is 90 kilograms, mass 2 is 95 kilograms. The velocity of our mass 1 is 5 meters per second going east, and our initial velocity for our mass 2 is 3 meters per second going north. Now for this type of problem, we have to draw two pictures, a before picture and an after. Okay, so here's our picture right here. We're going to make our up direction, which is north, positive, and our south direction negative, and our y direction. And we're going to make east be positive and west be negative, which is our x direction. So as in the problem, it says our mass 1 travels east initially with 5 meters at 5 meters per second, and our mass 2 travels north at 3 meters per second. This is right before our collision. Right after our collision, they join together. This is where the tackle starts taking place. They're together as one unit and drift off at a different direction at a different velocity also, which is the final velocity. Okay, so since this is a type of momentum problem where the initial momentum has to be equal to our final momentum, we have to use the momentum conservation of momentum equation, which is right here. P initial final is equal to P final, which is our mass 1 V1 initially plus mass 2 V2 initial plus our total mass, which is mass 1 plus M2 times V final. And as you can see, our V final has to be the same for both objects since they're both in an inelastic collision. They're both together after. So we can't, since this is a two-dimensional problem, we can't find V final directly like that. We have to split it up into our x and y components. So first we're going to solve for V final in the x direction, which we're going to put our mass 1 times V1 initial in the x plus mass 2 times V2 initial in the x is equal to our mass 1 plus M2 times our V final in the x. So we know that our second mass is traveling north, which is in the y direction, and not in the x direction. We're going to put this equal to 0 because it has no x component. So from there we're left with m1 times v1 initial in the x is equal to m1 plus m2 v final in the x. So we're solving for v final, which we're left with m1 times v1 initial in the x over m1 plus m2, which we could plug in our numbers now and have 90 times 5 over 90 plus 95, which is 185 right here. And our final velocity in the x direction is going to be 2.43 meters per second. So now we found it in the x direction, we have to find it in the y as well. So we're going to have go back to our original equation, and now we're going to have m1 times v1 initial in the y, which is set to 0 because our mass 1 only travels in the x direction. And we're also going to have m2 times v2 initial in the y is equal to m1 plus m2 times v final y. So since we said this was 0, we're going to be left with m2 times v2 initial in the y is equal to total mass times the final velocity in the y. We're solving for y, same steps as we took here. We're dividing by the total mass, and now we're going to have our mass 2 times v2 initial in the y times m1 plus m2, which right here we just plug in our numbers and we should get 1.54 meters per second. These are our final velocities in the x and in the y direction. So now that we found our velocity in the x and y direction, we can now finally find our final velocity at which both players move on to. And this is how pretty much we could find it. This is how pretty much our velocity looks. This is our final velocity. This is our final velocity in the x and in the y. So we can go by this problem and solve it two ways. One, by using the Pythagorean theorem, where we square both the y and the x and take the square root of it to find our v final. Or we could solve for our angle theta and be able to solve for it. So now, first I'm going to show you the way to solve it through the Pythagorean theorem, which we have our v final is equal to the square root of v final x squared plus v final y squared, which from there we solved for it earlier. We could just plug them in and we're going to end up with 2.88 meters per second. This is our final velocity right here. To check this, to solve it the other way, we use the tangent of theta is equal to our v final in the y over our v final in the x, which we're solving for theta now, so we're going to have to use the tangent inverse of our v final y over v final x, and we just plug in our numbers and we should be able to get the same answer, 2.88 meters per second. That is it for our problem B. So now it says to determine the mechanical energy that disappears as a result of collision. So now we're going to have to use our equations for energy, kinetic energy I should say. Since this is an inelastic collision, energy is not conserved because since both objects stick together, the energy from the whole system is lost and drifts off into other things, into sound or heat and other forms of that. So since our initial energy cannot be equal to our final energy, we're going to have to use this equation, which is the change in kinetic energy is equal to our kinetic energy in the final stage minus the kinetic energy in the initial stage, which now we can solve for separately. We have our KE initial, which is 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared, and by plugging in our numbers we have that, and we should be able to get 1552.5 joules as our initial energy. So now we solve for our final energy, which is 1/2 times m1 plus m2 times v final squared, which we plug in our numbers and we should be able to get 767.232 joules as our final energy. So now we plug these numbers back into this equation and we should end up with negative 785.268 joules, which that would be the energy that we lost in the collision. This should conclude our problem for number 26, chapter 9.